Hi, my name is Jerry Abraham. Today we will take a deep dive into BERT transformers. Hopefully, over the next few minutes, we will uncover what really happens under the hood. BERT stands for Bidirectional Encoder Representation from Transformers. This was developed by Google primarily for deep learning. BERT understands context of words in a sentence as it looks at it bidirectionally simultaneously. Traditional models read text in a single direction, but BERT has a bidirectional approach, enabling it to understand meanings, word relationships, and intentions. And it is pre-trained on a massive amount of data and primarily used for sentiment analysis, Q&A, language inference. I have broken my presentation into two parts. One is the foundation layer, and the second is the application layer. So let's look at the pre-trained model. So BERT is pre-trained on a huge amount of text like Wikipedia 2.5 billion words, books corpus 800 million words. Now we will look at two of the key models in BERT. One is the MLM and the second is NSP. MLM stands for Mass Language Modeling. Here it has to predict missing words from a context. So if you look at the sentence that's given here, the food was tasty and the service was excellent. So here certain words are masked at random and BERT has to predict those words. Next we have NSP, next sentence prediction. It has to essentially guess whether sentence B follows sentence A. So you have a pair of sentences given here. The customer left a bad review and B, the manager apologized the next day. So if it actually follows, BERT would say true. If not, it will say false. So in MLM, this trains BERT to understand deep language patterns, grammar, and meaning. And NSP, this helps BERT learn sentence level relationship, useful for Q&A and summarization. In stage 2, let's see what really happens. So if you have a sentence, it goes into the tokenization phase. Let's say if you have a sentence like this, I'm not happy with the dish, it tastes awful. So it is initially tokenized, special tokens are added. CLS is the classification token, SEP is the separator token. After this, it is converted into token IDs, essentially a list of integers, right? So the first step here in stage 2 is tokenization, where you have special tokens and then converted into token IDs. Now let's move into BERT embeddings, right? So the next stage that you have is the embeddings, where the tokens are converted into vectors. So you have the token vector, so the token embeddings rather, which captures the meaning of the word. The position embedding captures the order of the words in a sentence, and you have segment embeddings, where you have, if you have two sentences, it just says that sentence A is followed by sentence B. So these embeddings are added to the token embeddings. So these embeddings are essentially an array. It's a vector in a 768 dimension. So think of it in a 768 dimensions space. So it actually gives you coordinates in that space, right? So location in that dimension and also tells you the direction, right? Then these final embeddings actually goes into the BERT encoder, which is a 12 layer encoder. It also has a BERT also has a 24 layer encoder, right? So each of these token vector actually goes through the attention layer. Here, self attention allows each token to focus on other tokens in a sentence, helping BERT understand context and meaning based on the entire input, not just neighboring words. So, for example, if you look at this, the word bank, it helps him to understand the context. Is it river bank or is it savings bank? And finally, you get an output, which is a new vector, which one, you will have a contextual embedding, which is used by MLM, and you have a pooled output, which is used by NSP and also used for classification. So for example, if there were 5 tokens, you will have 5 vectors, each of size 768, and which will give us a contextual embedding. And you will also have a pooled output, which is of shape 1 into 768. This is the classification token also used by NSP. After the prediction is done, you will compute the loss and then train, right? So we use cross entropy loss. So this measures the difference between the predicted probability and the actual labels. So if the loss is high, the prediction is wrong. and if it is low, then it is correct. So that is how you actually quantify the error. Then you have the Adam optimizer. Adam optimizer will adjust the weight. After looking at the loss value, it will adjust the weight to minimize the loss. So that is the goal of the Adam optimizer, which is to minimize the loss. Let's look at two simple examples to understand this better. So here I have an example for cross entropy loss. Let's say the ground truth is that it is classified as positive and represented like this: positive, neutral, and negative. And you have a one hot encoder 100. The model predicts it as zero point 0.7, zero point 0.2, and zero point 0.1. So essentially it says 70% confident that it is positive, 20% neutral, and 10% negative. So cross entropy loss in plain words is how far is the predicted probability. So here it is 0.7% positive, but the actual label is 1, which is 100%. So if the model is confident and correct, we say the loss is low. If it is confident and wrong, we say the loss is high. Now to understand Adam optimizer, here is another example. So the sentence is food was amazing. We will look at just two features, food and amazing. Let's say the input vector is 1.2 and 0.8, right? So it says 1.2 is for amazing and 0.8 is the vector for food. So there are initial weights which are given to it, right? So based on the importance of those words in the sentence, the weights are given. So this is multiplied by this to give us a prediction. So you have an output of 0.0 minus 0.08. This passes through softmax, which is an activation function which is used in the fine layer for classification models to actually give you a probability. So you have your prediction, which is a probability. It says 70% confident. But the ground truth is actually it is 100% positive, right? So after this, you will have the gradient calculation done. So gradient basically tells the model how much and in which direction to change the weight, right? So the initial weights that we gave. So how much and in which direction the weight has to change to reduce the loss. So let's look at this. So the gradient calculation was done and it has come up with these two numbers, 0.5 and minus 0.1. So basically it tells that 0.5 is for weight 1 and minus 0.1 for weight 2. So it basically tells that 0.1 was where it contributed more to the error because it has a higher gradient over here. So we have to slightly reduce this. And minus 0.1, it says it didn't contribute much, right, to the loss, and we can slightly increase it. Now in the using the updated weights using Adam, it's simplified over here. You have your learning rates. So the weight 1, you have 0.2, which was the initial weight, and you have minus the learning rate into the gradient. You get this value, which is a new weight. And weight 2, this is the initial weight minus the learning rate into the gradient. So you have a new weight. So this is again multiplied with the input vectors, and you have a new output. This again goes to softmax, which is what I said is the activation layer, and you have the new prediction. So now you see that the loss is layered. So it goes through these iterations. So once the training is completed, so you save the weights are saved in the full BERT encoder in all 12 layers, and you have a package. Now this is actually available in Hugging Face. So you have the auto model dot from a pre-trained in BERT base uncased. So the auto model loads a full 12-layer BERT encoder with all pre-trained weights, and the auto tokenizer also there in Hugging Face dot from underscore pre-trained. Right, this has the exact words used in BERT pre-training. It has the word piece tokenization logic, and it has those special tokens like CLS and SCP. Right, so together they ensure that your inputs are processed the same way BERT has originally trained. Now this we can actually use in our line to make prediction, whether it is sentiment analysis, question answering, RAG embeddings. In fact, I have created a video on RAG plus Gen AI. Please do look at it. And entity extraction and classification. Now let's look at the application layer. Right, here is an example. You have the input sentence: I am not happy with the dish, it tasted awful. Right, so it goes through tokenization. So you have your special tokens, then it's converted into token IDs. Then it goes into the embedding where you have the token embeddings, positional embeddings, segment embeddings, essentially vector. Right, then this goes into the encoder layer, right, where you have two outputs, right? One is the contextual embedding, and you have the pooled output. So what goes over here? We have to use it for classification. So you will use the pooled output, which is a classification token, right? So this is what you get as the output. And so look at this. So it is 1, 2, 3, 4, 5. So based on where the highest number is, you say this is classified as 1 star. So that is how you do a sentiment analysis, right? So that brings us to the end of our presentation, right? I hope you've got to learn something on BERT during this deep dive session. Thank you so much for being with me on this video. Cheers. Have a great day. Bye-bye.